Now you can see my screen, right? Vibhavasti, you can see my screen, right? If not, then hello, hello. Hello. So no one is responding. Let me go ahead. If Z is a subring of a ring and R, then R is an integral domain. We will disprove this statement. Then next part. Where is this one? Each part. If there is a surjective ring homomorphism from Z to R, homomorphism Z to R, where R is any ring, R is any ring, then R is an integral domain. Tell me, this is true or false? Nagmani, tell me. At least unmute yourself so that I can feel someone is here. Otherwise, it's boring. Hello. Nagmani, can you hear me? Okay, leave it. If there is a surjective ring homomorphism Z to R, where R is any ring, then R is an integral domain we have to prove. So is this correct or not? This is obviously false statement, right? If take Z to Z mod 4Z, this is isomorphic to Z4, and this homomorphism is just a projection homomorphism. This is surjective. Phi mapping Z to Z mod 4Z. Phi is surjective, but Z4 is not an integral domain, right? The next part, F. If R is a subring of a field, then R is a field. This one is false. Subring of a field, then R is a field. If R is a subring of a field, then R is a field. So is this true or false? So how we will do this? So if R is a subring of field F, then R is a field. Okay. So take is this true or false? Since take let's say Z, Z is a subring of Q. Q is a field, but Z is not field. So this statement. So this statement is not true, right? Next question. Question number 6. Let I comma j be ideals in a ring R all correct statements. E I and j both prime, then the intersection j is always prime ideal of R. If I and j both prime, then intersection j is always prime ideal of R. Okay. How to prove this? Is there any participants? So I can ask them if there is some. Vibha Avasti, how we will prove this? Is this true or false? Hello. 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 I don't know. Can you hear me or not? No one is responding. I will assume that you can hear me. So let me go ahead. If I and j both prime ideal, then I intersection j is always prime ideal. We have to prove this one or disprove this one. So is this correct or not? What's your idea? If you want to give some suggestion, you can give. At least unmute yourself, talk something. Otherwise, why this is interaction session? This is just a boring session.
Hello.
Yeah.
Sir,
Hello. Yeah. Tell me. Okay. Take R is equals to ring of integers. I is equals to 2z. claim 6Z is not prime ideal in Z. How you will prove this? Take 3.2 belongs to 6Z equals to 6 belongs to 6Z, but 3 does not belong to 6Z and 2 does not belong to 6Z. This implies 6Z is not prime ideal. So given statement is false, right? So this one is false. So next one. Next is, if I and J both maximal, then I intersection J is always prime ideal. This one, B1. If I and J are both maximal, then I intersection J is always prime ideal. Is this true or not? Is this true or not? Vibha Avasthi, is this true or not? Avasthi, you are saying something?
Sir, here is network issue.
Okay, you have network issue? Hello? Okay. Take. Yeah. Yeah. I can. Yeah.
Here is created network issue, so I can't see your screen sharing. So questions I not understand.
Okay, fine. Okay, fine, no issue. But as we see in part A, that hello, yeah, tell me.
Yes, now here network issue is something well. So
Okay.
sir, I want sir one more. Please repeat.
Okay, so like the
Okay, sir.
first part is this. First part saying that if I and J both are prime ideal, then I intersection J is prime or not. Okay, so we have
Okay,
to
sir.
show, we disprove this statement. We prove that this is false. Like we take ring of integers and take two ideals 2Z and 3Z. Both are prime ideals, but I intersection J is basically 6Z ideal, because you can see 2Z is 0,
Yes, sir.
2, 4, 6, this kind of element. 3z is 3 is 6. Basically, multiple of 6 will occur in common, right?
Okay, sir.
Yeah. So I intersection j is 6z. But we proved that 6z is a not prime ideal. So I intersection j is not prime ideal. Now we have to see that if I and j both maximum, then I intersection j is always prime ideal. But we are disproving this one also. Take similar one, I equals to 2z, j equals to 3z. Now they both are also maximal, but as we see in part A that I intersection j is 6z, which is not prime ideal, right?
Yes, sir.
Okay, which is not prime. So this is false. C part. Now, phi mapping R1 to R2 be a ring homomorphism. If I is a prime ideal of R2, then phi inverse I is a prime ideal of R1. Morphism. If is a prime ideal of R2, then phi inverse I is prime ideal of R1. Is this true or false? What's your idea? Tell me.
Uh, sir, I have no, sir.
Okay. Okay.
Sir,
Yeah.
I missed the video, so I can't reply.
Okay. Fine. 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 Okay. Take I is a prime ideal of R2. Then we have to show phi inverse I is a prime ideal of R1. Okay. So and let A comma B belongs to phi inverse I. Sorry. A dot B. AB belongs to phi inverse I. That means this implies okay, this implies phi of AB belongs to I. This implies we have to show that A belongs to phi, either A belongs to phi inverse I or B belongs to phi inverse I. Okay. AB belongs to phi inverse I. This implies phi AB belongs to I. Okay. This implies phi A dot phi B belongs to I. But I is a prime ideal given. But since I is a prime ideal, this implies either phi A belongs to I or phi B belongs to I or both, right? So if so this implies either A belongs to phi inverse I or B belongs to phi inverse I. This implies phi inverse I is a prime ideal, right? So we are done. So this statement is a true statement.
Yes, sir.
Yeah. So next part. If phi mapping R1 to R2 be a ring homomorphism, I is a maximal ideal of R2, then phi inverse I is a maximal ideal of R1. If phi mapping R1 to R2 be a ring homomorphism, if I is a maximal ideal of R2, then phi inverse I is a maximal ideal of R. Is this true or false? You can respond. You can respond. Nagmani, you can respond.
Sir, the 1 second, sir. I read the question again one time, sir.
Okay. So if phi mapping R1 to R2 be a ring homomorphism and I is a maximal ideal of R2, then phi inverse I is a maximal ideal of R1. Is this true or false? In second part, we proved that if I is a prime ideal of R2, then phi inverse I is a prime ideal of R1. So now he is asking about maximal. So if I is a maximal ideal of R2, then phi inverse I is a maximal ideal of R1. Is this true or false? Okay.
No idea, sir. Sorry, sir.
Okay. Take ring homomorphism Z to Q, inclusion ring homomorphism. So take here maximal ideal 0. So now inverse image of 0 should be only 0 ideal, but
Yes.
0 is not maximal in Z, right?
Mm.
So this statement is false.
Okay.
So false. Inverse image of a prime ideal is a prime ideal, but inverse image of a maximal ideal is not maximal, need not be maximal, right? So this is the true statement we prove. And last one is, if phi mapping R1 to R2 be surjective ring homomorphism, if I is a maximal ideal of R1 containing the kernel phi, then phi I is a maximal ideal of R1. Right? Let me write. If phi mapping, let phi mapping R1 to R2 be a surjective homomorphism, ये surjective ring homomorphism if I is a maximal ideal of R1, containing the kernel phi, then phi I is a maximal ideal of R. Then phi I is maximal ideal of R2. So tell me, is this true or not? Nagmani, Viva, both can respond.
Mm.
So tell me, is this true or false? Phi mapping
True,
R1
sir.
true.
Yes, sir.
Give me proof.
Above one example, sir. EJ tends to.
This is
False,
not
sir.
surjective, right?
False, sir.
False. Why? Give me counter example.
Z tends to Q, sir. Is the ideal identity mapping, sir.
Z to Q, right?
Is the Z to Q identity mapper.
But it is not surjective, right? It is injective but not surjective. It is asking about surjective.
Oh. Another one examples. Wait, sir.
Yeah, sure.
அடியில் இருக்க பாக்ஸ் இருக்கு.
Tell me. No idea.
No, sir.
Okay. So try to use first isomorphism theorem. What it says. Do you know first isomorphism theorem?
Again one time recall, sir, please, sir.
Okay, fine. If first isomorphism theorem, if phi mapping R1 to R2 surjective ring homomorphism, then R2 is isomorphic to R1 mod kernel phi. Now this is the statement.
Okay, sir.
So now tell me. So now your statement is this: phi mapping R1 to R2, which is isomorphic to R1 mod kernel phi, right?
Mm.
Now you have given I is a maximal ideal of R1 containing kernel phi. Given I is a maximal ideal of R1 containing kernel phi, then phi I will contain kernel phi and by correspondence theorem phi I will be maximal ideal of R1 mod kernel phi isomorphic to R2. This implies phi I is maximal ideal of R2. So done. This is the done of this practice assignment. Also, all the parts are done. So with this, I want to end this session. So if you want to say something or comment something, you can say.
Hello.
Tell me. You are saying something? If not,